Hello everyone, this is Firoz Nadav. In this video, we will see design of beam for shear. We will not go into great detail what is shear, how to understand shear in the beam. Someday I will talk about that aspect also. But here we will only see uh, the design steps that are there in the design of beam for shear, because students they have their exam, and for that I am making this video. Okay, so first step in the design of beam for shear is to find tau v. Okay, so what is tau v? Tau v is nominal shear stress, or simply you can call it as shear stress. It is equal to Vu by Pd. What is Vu? Vu is shear force. So this is the very first step. The unit of tau v is Newton per mm square. Okay. Then we have to find tau c. Okay, tau c depends on two values, and those two values will be given in the problem. Okay, it depends on grade of concrete, and it also depends on percentage of reinforcement in the beam. So you must know these two value in order to find tau c, and tau c is calculated, or tau c is determined, or tau c is taken from IS 456-2000, table number 19, I think, table number 19, page number 73. Okay, so from this table we are determining the value of tau c. So after getting the value of tau v and tau c, what is the third step? Third step is to compare tau v and tau c. Tau v and tau c. If tau v is less than tau c, okay, so first I will tell you what is tau c. Tau c is the shear strength of the concrete, or you can say the shear capacity of the concrete. If you have some value of tau c, and you can say that from looking at the value that is the shear capacity of the concrete. Okay. In the third step, we have to compare tau v and tau c. If tau v is less than tau c, then we can say that we can say that shear reinforcement is not required. Shear reinforcement is not required. But that does not mean that we are not providing any shear reinforcement. If this is the case, then what we do, we provide nominal or minimum shear reinforcement. Minimum shear reinforcement. Shear reinforcement. Okay. The point is that if tau is less than tau c, shear reinforcement is not required, because concrete is capable of resisting the shear. But then also IS code says that we have to, in case of beam, we have to provide the minimum shear reinforcement, minimum stirrups. So what are the minimum stirrups? It is given in IS code. We have three formulas. Okay, SV spacing. Minimum stirrup means maximum spacing between the stirrups. Maximum spacing. Okay, so we have three formulas to to provide minimum reinforcement, minimum shear reinforcement. SV means spacing. Okay, SV equal to 0.87 Fy ASV divided by 0.4 B. Fy is grade of steel, ASV is area of the stirrup. So you see stirrups are provided like this: two-legged, three-legged, four-legged. Okay, so two-legged means if this is the stirrup that you have provided, this is two-legged 8 mm bar. Okay, two-legged 8 mm bar. So for this ASV will be 2 into pi by 4 into 8 square. So ASV is nothing but area of stirrups. Second is SV equal to 0.75 D. D is effective depth of the beam. Third is SV equal to 300 mm. So these are the provision to provide the minimum shear reinforcement. Okay, so what we have to calculate the value of spacing by using by these three formulas, and we have to adopt the lesser one, adopt the lesser one, lesser one. Okay, one more thing, in any case the spacing should not be more than 300 mm. This should also you have to note, in any case spacing should not be more than 300 mm. If tau v is greater than tau c, then we can say that the concrete is not capable of resisting the shear, and here we have to write one statement: shear reinforcement must be provided, shear reinforcement must be provided. Okay, so how to provide shear reinforcement? We have four ways by which we can provide the shear reinforcement. We will discuss one by one. Number one is vertical stirrups. Simply we have to provide vertical stirrups. Okay, so if you if you have a look on the detailing of the beam, or you have seen the longitudinal section of the beam with respect to its detailing, you will understand that we have bars at the top and also bars at the bottom. We are getting bars at the top and bars at the bottom when we design the beam for flexure. Okay, so here what we are doing, we are simply providing vertical stirrups like this, and these vertical stirrups will resist the shear. Okay, this is one way, and this is the common way of providing the shear reinforcement. Second is vertical stirrups and group of bars curtailed at same cross section. Group of bars curtailed. Curtailed means bent up. Curtailed at same cross section. What is the meaning of this? You see, uh, okay, so let us say that you have four bars at the bottom, and what you are doing, you are providing, you are taking two bars at the top at some cross section. You are taking two bars from the bottom to the top. You are curtailing the bars. Okay, so at this point you have four bars at the bottom, and at this point you have only two bars at the bottom. So where are the two bars? Two bars are curtailed and at the top, they are going at the top. Okay, so here this bent up bars, these curtailed bars will also resist the shear force. Okay, this will also act as shear reinforcement. That is the point. Okay. Third way of providing shear reinforcement is same vertical stirrups. Group of bars are curtailed at different cross section. Different cross section. Okay, so you see some bars you have curtailed at this cross section, some bars you have curtailed at this cross section. So basically what you are doing, you are curtailing the bars at different cross sections. Okay, so whichever bars are curtailed, they will also resist the shear. That is the point. Third way of providing shear reinforcement is inclined stirrups. Providing inclined stirrups. Inclined stirrups. I think we are no longer providing inclined stirrups. How these are provided? If this is the beam and these are the reinforcement at the top and the bottom, what you are doing, you are just simply providing inclined stirrups like this, and this will take the shear reinforcement. Okay, so when we are providing the shear reinforcement as the vertical stirrups, what we have to do in this, you see, we will have to find tau v equal to vu by bd. What is VU? VU is the shear force. If this is the beam and if it is subjected to UDL over the entire span, okay, the intensity of the UDL is W kilonewton per meter. L is the length of the beam. VU equal to, which is shear force, equal to W L by 2. So in this way we will have to find VU shear force in the beam, and tau V is nominal shear stress. After finding tau V, we have to find tau C. Okay, so tau C can be taken from IS 456-2000, table number 19, page number 73. It depends on two value. We should know the grade of concrete, and we also have to know the percentage of reinforcement in the beam. So by knowing those two value, we can determine the value of tau C. Okay, so after determining tau V and tau C, we have to compare. Let's say tau V is greater than tau C, shear reinforcement is required, and we are going for vertical stirrups. We are providing shear reinforcement as vertical stirrups. Okay. So what we have to do here, first we have to find the net shear force. Net shear force in the beam. What is that? I will tell you. VUS, net shear force. VU is shear force, okay, and some of the shear force is resisted by the concrete. Okay, so VUC is the shear force resisted by the concrete. VU is shear coming on the beam, and VUC is shear force resisted by the concrete, and VUS is net shear force for which the shear reinforcement shall be designed. Okay, so VU you will get from this. How to calculate VUC? I will tell you. VUS equal to VU minus VUC is tau C into BD. You will get the value of VUS, net shear force. Now after this we simply have to provide the spacing. Shear reinforcement is required here. So how to calculate spacing? We have four different formulas in this particular case. Spacing equal to SV, number one, for this is number one formula, 0.87 Fy ASV into D divided by VUS. VUS you are getting from this formula. Okay. Second, SV equal to, most of the time you shall be getting the spacing with respect to formula number one. Number two is 0.87 FYASV divided by 0.4 B. Third one is SV equal to 0.75 D, and fourth one is SV equal to 300 mm. So lesser of the four shall be taken as the spacing for the shear reinforcement. Okay, so if you are providing the shear reinforcement by curtailing the bars, you are providing vertical stirrups, and also you are curtailing the bars, then what we have to do, we will see here. In that case, we have to find VU. You know how to find VU. Then we have to find VUC. Okay, so VUS equal to VU minus VUC. You know this. Okay. So here you see the curtailed bars is also resisting the shear force. This is the shear force that is coming on the beam. Okay, and this is the shear resisted by the concrete. And one more thing is there, shear is also resisted by the curtailed bars, bent up bars, and we are required to find the shear resistance by the curtailed bar. It is denoted by VUS dash equal to VS dash equal to 0.87 Fy ASV dash into sine alpha. What is ASV dash? ASV dash is area of the curtailed bars. ASV dash is area of curtailed bars. For example, if you have taken two bars at the top, means you have to just simply calculate the area of two bars, curtailed bars. Alpha is at what angle those bars were curtailed, at what angle the bent ups were provided. Okay, so you have to find VUS. So here the net shear force is is net shear force is VUS star, okay, equal to VU VUS minus VUS dash. One more thing you have to remember here, when you are calculating VUS should not be greater than, so VUS should not be greater than VUS by 2. Okay, you will get VUS from this formula. After that you have to find VUS dash. You have to compare, it should not be greater than VUS by 2. If it is greater than VUS by 2, then what you have to do, you have to take VUS dash equal to VUS by 2. This thing you have to take. Okay, so now this is the net shear force for which we have to design the vertical stirrups. Okay, so here spacing will be SV equal to 0.87 Fy ASVD divided by, instead of VUS here it will be VUS star. Okay, second will be same, second, third, fourth will be same. So what we have to do, we have to take lesser value out of 4, lesser value out of 4. Okay, so if you are providing shear reinforcement by case number 3, what is case number 3? Vertical stirrups and group of bars curtailed at different cross section. What we have to do? Again we have to find VU, then we have to find VUS. So what is VUS? VUS equal to VU minus VUC. VU minus VUC is tau C into BD. Okay, so here the bars are bent up, bars are curtailed at different cross section. So there will be some resistance by the curtailment of the bar. Okay, so we have to find what are the resistance provided by the curtailment of the bar. VUS dash, here the formula of VUS dash will be different. Okay, 0.87 Fy ASV dash into D divided by SV dash into sine alpha plus cos alpha. Okay, so ASV dash is the area of the curtailed bar. You can say total area of the curtailed bar. What is SV dash? Okay, if this is your beam, if this is your beam, you have bars at the bottoms. So what you have done, you have provided the curtailment of the bar at different cross section. At this cross section you have provided, and also at this cross section you have provided. Okay, so you are providing two curtailment of the bars at different cross sections. So SV is nothing but spacing of bent up bars along the length of the beam. This distance is nothing but SV dash. Okay, here also after calculating alpha is the angle of the curtailment. Okay, ASV dash is the same thing as we have seen in the previous case. All the things are very clear here. Okay, so VUS dash should not be greater than VUS by 2. If it is greater, then it should be equal to VUS by 2. We have to take this value if it is greater than VUS by 2. Okay, so here also we have to determine VUS star. VUS star. Okay, so what is it? VUS star, VUS minus VUS dash. Spacing, the formula of the spacing will be same as we have seen in the previous case, as V equal to 0.87 Fy ASV D divided by VUS star. Formula number 2, 3, 4 all will be same, and we have to take the lesser value. We have to take the lesser value. Okay, see problem. Design the shear reinforcement for the rectangular beam of dimension 350 mm by 500 mm effective, provided with the tensile reinforcement comprising 4 bars of 25 mm diameter. The beam is subjected to maximum factored shear force of 400 kN. The materials are M20 and Tor steel. Refer table. Okay, so you see, they have given this problem, they have given the reinforcement, cross section, and also they have given the factored shear force. Okay, so you see, when we are dealing with limit state method of design, always remember that whatever shear force that we will calculate, it should be factored one. Here directly they have given, sometimes they will give you UDL, from that you have to find uh, the shear force. Okay, then you have to make it factored by multiplying 1.5. And also you see, they have not mentioned any curtailment of the bars. They have not mentioned in the problem any bent up bars. So what we have to do here, we simply have to provide the vertical stirrups. Okay, and this table is the table number 19, page number 73 of IS 456. Sometimes in the problem itself they will give you the table, and from that table you have to find the value of tau c. Okay, for M20 grade concrete they will give you the value of PT for different value of tau c. Okay, so effective cross section is given to you, AST is given to you, you have to find the AST value. Okay, VU factored shear force is given to you, that is 400 kilonewton. Tau v equal to, first you have to find tau v, we have seen the step. Tau v equal to VU by B into D. V should be in Newton. Okay, so tau v value comes to 2.28 Newton per mm square. So we also have to find tau c max value. It depends on grade of concrete, from table number 20, page number 73. Okay, so you see, tau v should not be greater than tau c max in any case. In any case, if it is greater than tau, we have to increase the depth of the beam. Okay, we cannot simply rely on shear reinforcement. If tau v is greater than tau c max, then we have to increase the depth of the beam. Okay, tau c max is 2.8 Newton per mm square. It is less than tau c max. Tau v is less than, what is tau v? Tau v is 2.28 and tau c max is 2.8. Okay, tau v is less than tau c max, and proceed with the given depth. Whatever depth they have given, we have to proceed. Now what we have to do, we have to find tau c from table number 19, or table, they have given the table. From this table we have to find the value of tau c. Okay, it depends on, already I have told you, it depends on percentage of tensile reinforcement and grade of concrete. So you have to find PT. AST already have calculated, AST by B into small d into 100. Okay, the percentage of steel is 1.12. Okay, so you see what value we have, the percentage value we have 1 and 1.25. It is between 1 and 1.25. Okay, so in that case what we have to do, we have to do the interpolation. We know the value of tau c for 1, we know the value of tau c for 1.25, but we don't know for 1.12. Okay, so here we have to interpolate, and we have to take the value of tau c for PT 1.12. So this is the formula by which you can do interpolation, or simply you can use the calculator. Tau c is coming 0.6 644 Newton per mm square. Tau v is greater than tau c, hence shear reinforcement is required. Okay, so we have to find VUS. Here I have written VS. It can also be taken as VUS. VS equal to VU minus VC. What is VC? VC is tau c into B into D. In the design step, I have written it as VUC. This is VUS, and this is simply VU, and this is VUC. Okay, VU is given to you, and how to find VUC? Tau c into B into D. You will get VUS. VUS. Okay, so after getting VUS, we can provide the shear reinforcement. Before that, you have to assume the diameter of the stirrups and what leg of the stirrups that you are going to provide, whether you are going to provide two-legged stirrups or three-legged stirrups. So most of the time, generally speaking, we are only providing two-legged 8 bar stirrups. Okay, we have to determine spacing. At what spacing you will provide the stirrups. So we have this formula: SV equal to 0.87 Fy ASV into D divided by VUS. So you are getting spacing equal to 63.17. Okay, so you see, generally speaking, spacing should not be less than 100 because it will create practically difficulty while concreting. So you see, and more than this we cannot provide because this is the required. It should be less than 63. Okay, and what we say, we should, the spacing should not be less than 100 So what we have to do, we have to increase the leg. We have to provide 3 leg of 10 bar. Okay, so here simply what you have to do, see, 0.87 into Fy into ASV. ASV, here we are changing the ASV. In the previous case, it was two-legged, 2 into pi by 4 into 8 square. Here, because the spacing is very less, we are increasing the leg, we are increasing the stirrups. Okay, so here ASV is 3 into pi by 4 into 10 square. Okay, so all the things are clear. The spacing is 148.07. So there are other formulas also. Formula number 2, 3, 4. By using formula number 2, the spacing is 607. Formula number 3 gives you 375. Formula number 4 is simply 300 The lesser value is 148.07. So what we have to do, provide 3-legged 10 bar at the rate 140 center to center. The spacing should be less than this, should not be greater than this, because this is the required spacing. Okay, so we will see the next problem. A rectangular beam 230 by 450 effective is reinforced with 6 bars of 16 diameter out of which 2 bars are bent up at 45 degree. So here they are telling us they have provided bent up bars, they have curtailed some bars, they have curtailed 2 bars. Determine shear resistance of bent up bars. Shear resistance of bent up bars is VUS dash. Okay, and additional shear reinforcement required if the ultimate shear force is 300 kilonewton. Design the shear reinforcement, adopt M20 and FE415. 10 marks, May 2014. Okay, so they have given bent up bars. 2 bars are bent up at 45 degree. Alpha is given to you. Shear force is ultimate shear force. Simply it's factored shear force. You don't have to calculate the shear force, factored shear force. They have given 300 kilonewton, and this table is given to you to find tau c. So first we have to find tau v. Tau v equal to VU by VD. VU is given to you, it should be Newton. Okay, tau v equal to 2.89 Newton per square. Now you see, after this we have to find tau c max from table number 20, page number 73, IS 456. Tau c max depends on grade of concrete. For M20, tau c max is 2.8. So I told you, in any case tau v should not be greater than tau c max. If it is greater than tau c max, then we have to increase the depth. Okay, so what we will do, taking effect, what effective depth they have given? Effective depth they have given is 450 mm. and we can increase the effective depth. We can take, because tau v is greater than tau c max. So in order to avoid this phenomena, we have to increase the effective depth. Okay, so when we take 480 mm as effective depth, tau v equal to 2.71, which is below 2.8, which is below tau c max. Okay, now we have to find tau c. Tau c, to find tau c, we have to find pt, percentage of steel. Okay, ast by bd into 100. You can do that, you will get this percentage of reinforcement. And uh, you see, pt is between 0.5 and 0.75. You have to interpolate and you will get the value of tau c, which is equal to 0.572 newton per mm square. You got the value of tau v, you got the value of tau c. Compare tau v and tau c. Here tau v is greater than tau c, shear reinforcement must be provided. So VUS equal to VU minus VUC, 300 into 10 to the power 3 minus tau c into B into D. So here you are getting VUS. Okay, we got the value of VUS, that is 236.85 into 10 to the power 3 Newton. Okay, so we have to determine VUS dash. What is VUS dash? It is the shear capacity of the curtailed bar. It is the shear capacity of bent up bars. We know the formula to find the shear capacity of the curtailed bars. VUS dash equal to 0.87 Fy ASV dash into sine alpha. So we have seen that how many bars they have curtailed 2 bars of 16 mm diameter. So ASV dash is nothing but area of curtailed bars. Okay, okay, so 0.87 into Fy 415 into 2 bars of pi by 4 into 16 into alpha. Alpha is also given in the problem, that is 45-degree sine alpha. So VUS dash equals to 102.67 into 10 to the power 3 Newton. Okay, so this is what VUS dash you are getting. Now after finding VUS dash, what is VUS dash? First you have to see VUS dash is the shear capacity of the curtailed bars. So after finding VUS dash, you have to check VUS dash should not be greater than VUS by 2. So this is the value of VUS dash and this is the value of VUS, and 102 is not greater than uh, uh, half of this value. Okay, so whatever value of VUS dash we got, we can take it. After that we have to find VUS star. VUS star equal to VUS minus VUS dash. So VUS is 236.85 into 10 to the power 3. All the things should be Newton, minus 102.67 into 10 to the power 3. After solving this, you will get the value of VUS star, which is equal to 134.18 into 10 to the power 3 Newton. Okay. Okay, so we got the net value of shear force in the beam. We have deducted the shear capacity of the concrete. We have also deducted the shear capacity of the curtailed bars. Okay, so whatever the shear capacity that we have, shear force, the net shear force that we have to use it to calculate the vertical stirrups. Okay, okay, so what we have to do now, we have to find the spacing of the vertical stirrups. For that, first we have to assume the what vertical stirrups we are providing in the beam. So we'll assume that we are providing two-legged 8 mm bar. Most of the time you will be providing this as a shear reinforcement. Okay. So number one, spacing SV spacing equal to 0.87 Fy ASV into D divided by VUS star. Okay. Just substitute the value 0.87 into Fy 415 into ASV. We are providing two-legged 8 mm bar. 2 into pi by 4 into 8 square into D is 480 divided by VUS star. We got the value of VUS star 134.18 into 10 to the power 3. Okay. After solving, SV value is 129.86 mm. We have three more formulas and we have to take the lesser value of the spacing. Okay. Second formula is SV equal to 0.87 into 415 into ASV 2 into pi by 4 into 8 square divided by 0.4 B, zero point 0.4 into 230. This is coming as 394 mm. Third one will give you SV equal to 0.75 D, will come as 360 mm, and fourth is SV equal to 300 mm. Okay, so lesser of the four is this value. You can provide shear reinforcement, provide shear reinforcement or two-legged 8 mm bar at the rate 120 mm center to center. So in this way you have to do the design of shear reinforcement. Thank you for watching this video. Thank you very much.